Imagine a motor that can spin up to 23,000 revolutions per minute and produce a level of power that in the past only Formula One race cars could achieve. Now picture that motor installed in your Tesla. How did Tesla manage to create such revolutionary electric motors that have made its cars the fastest in the world? From asynchronous motors to the innovative Plaid Carbon-Wrapped versions, today we will dive into the world of technology that is reshaping the automotive industry forever. Are you ready to discover what is inside the most powerful electric motors of our time? Then let us get going. Asynchronous or induction motors were installed on Tesla Model S and Tesla Model X in their earlier versions. Synchronous motors with permanent magnets are used in Tesla Model 3, Tesla Model Y, and later versions of Model S and Model X. Wound rotor motors represent an enhanced technology that combines the benefits of the previous types. Each of these motors has its own unique aspects in manufacturing. Before initiating production, Tesla engineers design the motor using modern modeling software. The design process considers the materials for magnets and windings, the shape of the rotor and stator for maximum efficiency, the cooling system to prevent overheating, the balance of weight, and the positioning of the motor in the car. After completing digital modeling, prototypes are produced and tested under laboratory conditions. Now let us move on to the stage that focuses on the key components. The first component is the stator. It is the heart of the electric motor and the stationary part of the motor, containing copper wire windings. The stator core is made of many thin layers of electrical steel, which helps reduce energy losses from eddy currents. These steel sheets are cut by laser cutting or stamping. The sheets are assembled together and pressed into the form of the stator. The next step is the coil winding process. Automated winding is utilized, along with a precise calculation of the number of turns. In order to boost efficiency, hollow copper wires with coolant flowing inside are used. After the winding, vacuum impregnation with varnish takes place to protect the windings from overheating and damage. We then proceed to the stator assembly stage. The windings are connected to electrical contacts. Temperature sensors are installed to monitor heating. The completed stator is subjected to quality control and testing. The rotor is the moving part of the motor. Tesla uses two types of rotors. An asynchronous rotor with a squirrel cage is employed in induction motors. It is made of aluminum or copper by casting the metal into a mold. A rotor with permanent magnets is used in Tesla's synchronous motors. It contains magnets based on rare earth metals, creating a strong magnetic field. As with the stator, a multi-layer steel structure is used for manufacturing the rotor. The steel sheets are cut and either glued or pressed together into the shape of the rotor. Neodymium magnets are inserted into the rotor body. The magnets are secured by adhesive or mechanical fasteners so that they can withstand rotational speeds of up to 20,000 revolutions per minute. Because the rotor spins at high velocity, perfect balancing is essential to avoid vibrations. The rotor is tested on specialized equipment that automatically adds or removes material to adjust the balance. The next stage is motor cooling. Tesla employs liquid cooling for its electric motors. Coolant circulates through channels in the motor housing, carrying away excess heat. This enables the motor to function at high power levels. The rotor is mounted on bearings for minimal friction. The stator and rotor are placed inside the motor housing. All components are connected according to the design. A controller operates the motor by regulating power and rotational speed. Metal oxide semiconductor. Field effect transistors, or insulated gate bipolar transistors, are employed to convert electric current. We now move on to the final step, which involves filling the system with cold fluid. The coolant is introduced into the cooling system and checked carefully for leaks. Following assembly, every motor undergoes an extensive battery of tests. A no-load test verifies smooth rotation. A load test evaluates efficiency and energy consumption. A thermal test stresses the motor under maximum loads. A noise test measures noise and vibration. Only after passing all these tests successfully does the motor proceed to the production of Tesla vehicles. Manufacturing Tesla's electric motors is a high-technology process that integrates advanced engineering approaches, automated manufacturing, and sophisticated testing methods. Tesla continually improves its motors, making them more efficient, more compact, and more powerful. This technology lets Tesla produce electric vehicles that outdo the competition in power, range, and reliability. The story of how Tesla developed electric motors for its cars is one of innovative technology, risk-taking, and the relentless efforts of engineers. It all started with an ambitious plan to revolutionize the automotive industry, and although initially the company did not produce its own motors, it ultimately became a leader in this domain. Tesla Motors was founded in the year 2003 by a group of engineers, which included Martin Eberhard, Mark Tarpenning, Ian Wright, Jeffrey Brian Straubel, and the future chief of the company, Elon Musk. The main vision was to create an entirely electric car capable of competing with conventional gasoline-powered vehicles. At that time, electric vehicles did exist, but they were slow and inefficient. That was when the Tesla team decided to utilize an asynchronous electric motor, originally patented by Nikola Tesla in the year 1888. Tesla's first electric motor was developed using technology from a company named AC Propulsion, which was creating high-powered electric motors for electric car prototypes. Tesla established a licensing deal with AC Propulsion and adapted its technology for its first model, the Tesla Roadster of the year 2008. This was a three-phase asynchronous motor featuring a rotating magnetic field. It was manufactured with an aluminum rotor, which provided excellent efficiency. The maximum output was 248 horsepower, enabling the Roadster to accelerate to 61 miles per hour in 3 9/10 seconds. Despite the success of this first vehicle, Tesla encountered difficulties with component supplies. The motors were made at external factories, and quality control was lacking. This pushed the company to consider setting up its own production lines. Transitioning to in-house production took place from the year 2010 to the year 2012. When Tesla started developing the Tesla Model S, it became clear that the company needed to manufacture its own electric motors. There were multiple reasons for this. The first reason was cost, since sourcing motors from external suppliers was expensive. Tesla also wanted a highly efficient motor designed to meet its specific requirements, meaning the design had to be optimized. Quality control was the third reason, because in-house production allowed the company to oversee every aspect of manufacturing. In the year 2010, Tesla purchased a plant in Fremont, California, previously owned by General Motors and Toyota. This was a pivotal milestone in scaling up production. In the year 2012, the Tesla Model S became the company's first vehicle to use Tesla's in-house electric motor. It was more powerful and more efficient than the previous generation's motors. The Tesla Model S motor of the year 2012 represented a breakthrough in technology. It was created using asynchronous induction motor principles, with a copper rotor instead of the aluminum rotor that was in the Roadster. The copper rotor raised efficiency and diminished heat losses. The performance version delivered 416 horsepower, enabling acceleration to 61 miles per hour in 4 4/10 seconds. This model drew global attention, and Tesla expanded rapidly thereafter. Let us examine the newer generations of motors from the year 2017 to the year 2020. Although asynchronous motors remained efficient, Tesla's engineers began exploring new motor designs. In the year 2017, during the development of Tesla Model 3, the company chose to adopt synchronous motors with permanent magnets. The Tesla Model 3 motor, starting in the year 2017, is a synchronous motor with permanent magnets. This made the motor smaller, lighter, and more efficient. Neodymium magnets helped reduce energy consumption. The refined cooling system enhanced reliability. This motor became standard in Tesla Model 3 and Tesla Model Y. However, Tesla did not stop using asynchronous motors and continued installing them on the front axle of Tesla Model S and Tesla Model X for dual-motor versions. Tesla pushed forward and introduced its Plaid Carbon-Wrapped Rotor technology, which premiered in the year 2021 in Tesla Model S Plaid. Plaid Carbon-Wrapped Motor is a revolutionary solution. It utilizes a carbon wrapping on the rotor, enabling incredibly high speeds of up to 23,000 revolutions per minute. An improved cooling system endures extreme stresses. The Tesla Model S Plaid can accelerate to 61 miles per hour in only 1 99/100 seconds, making it the fastest production electric car in the world. This technology was entirely developed by Tesla's engineering team and is unmatched by any competitors. Manufacturing electric motors for Tesla cars is a sophisticated and advanced process, encompassing pioneering research, modern simulation, automated assembly, and meticulous testing. Tesla gradually evolved from employing asynchronous motors in its early models to integrating state-of-the-art synchronous motors with permanent magnets and the revolutionary Plaid Carbon-Wrapped Rotor. Through continuous enhancements of its technology, Tesla has produced motors that combine outstanding efficiency, power, and compactness. This enables its electric vehicles to surpass competing models in acceleration, energy consumption, and reliability. Tesla's decision to make electric motors in-house allowed the company to manage quality, reduce costs, and refine designs, proving to be instrumental in its expansion. The unwavering drive toward innovation and the pursuit of new advancements solidify Tesla's role as a leader in electric transportation, shaping the future of the automotive industry. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress, so there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Every year, more than 500 billion matches are produced worldwide. That means around 16,000 matches ignite every second. But have you ever wondered how these tiny wooden sticks go through a complex manufacturing process before they end up in your hands? Today, we are diving into the fascinating world of match production, from selecting the right wood to applying the chemical coating that allows them to ignite with a single strike. You will learn how modern factories produce millions of matches daily, what materials they use, and why matches continue to thrive in the market even in the 21st century. The matches we are familiar with first appeared in the 19th century. Let's take a detailed look at each stage of match production. I will tell you all about it, from raw material selection to packaging the final product. The primary material for matchsticks is wood, carefully chosen for its properties. Softwood species are mostly used. Aspen has a uniform structure, is easy to process, does not crack, and provides consistent burning. Poplar is known for being lightweight and widely available. Pine is used less frequently due to its high resin content, but in some regions, it is carefully treated to remove the resin before use. Many manufacturers aim to use waste from the woodworking industry, reducing costs and making production more eco-friendly. The wood is stripped of its bark, sorted, and cut into transportable logs before being sent to the factory. At the factory, the wood is loaded into special drums for cleaning. The logs are then sliced into thin sheets, resembling ribbons. This is done using precision machines with adjustable blades. The ribbons undergo thickness uniformity checks since the quality of the final match depends on it. After slicing the ribbons, they are cut into individual matchsticks. On average, a standard match measures between 1.65 inches and 1.77 inches in length, with a thickness of approximately 0.79 inches. Tell me, did you just measure that too? I do not want to be the only one doing it. The blanks then go through a drying system, reducing their moisture content to an optimal level, no more than 6 or 8%. For additional protection, the blanks are treated with antiseptic solutions to prevent mold, fungi, and insect damage. After this treatment, the matchsticks move to the assembly conveyor. The chemical mixture for match heads is prepared in separate facilities. It is a complex combination of several key components. Oxidizers release oxygen during combustion. Sulfur or other flammable substances ensure stable burning. Phosphorus is the main element that enables instant ignition upon friction. Dyes give the heads their characteristic colors: red, green, black, and more. Adhesives bind the components together. The ingredients are mixed in specialized equipment, and the finished mixture is poured into storage tanks. For worker safety and to prevent spontaneous combustion, all operations take place in explosion-proof rooms with strict temperature control. By the way, did you know that in the year 1826, English pharmacist John Walker invented friction matches? His friction matches consisted of a stick coated with a mixture of antimony sulfide and potassium chlorate. Then, in the 1830s, Frenchman Charles Sourier improved them by using red phosphorus, which was less toxic and safer than yellow phosphorus. These matches could ignite only when struck against a specially prepared surface on the box, becoming the prototype of modern safety matches. After applying the chemical mixture, the matchsticks are sent to drying chambers. Here, they undergo a drying process that lasts approximately 2 or 3 hours. These chambers maintain a controlled temperature, ensuring the mixture solidifies evenly. This treatment gives the match heads the necessary strength to prevent crumbling or flaking, even during long-term storage or transportation. This stage is crucial since it forms the core functional part of the match, the head, which ensures its usability and durability. Thanks to modern technology and rigorous quality control, the final product is not only convenient, but also entirely safe for users. While the matches are drying, a separate production line manufactures matchboxes. Cardboard is used, going through several steps, which we will now explore together. Step 1. Cutting sheets into blanks. Step 2. Printing labels, which may include either simple manufacturer information or colorful designs depending on the order. Step 3. Forming the boxes using specialized machines that fold and glue them together. Next, a special abrasive coating is applied to the inner side of the matchbox. This mixture of phosphorus, glue, and quartz sand ensures match ignition. Afterward, the dried matches move onto a conveyor belt, where they are cut to a perfectly uniform length. Then, precision dosing machines distribute the matchsticks into the boxes. Each box is filled with an exact number of matches, usually 40, 50, or 100, depending on the format. Once filled, the boxes are automatically sealed and sent to the packaging line for shipping and storage. The finished match blocks are labeled and sorted onto pallets before being loaded onto trucks for delivery to stores or wholesale suppliers. Now we are in the final stretch of match production, the concluding stage that wraps up this long, intricate, and carefully planned process. At this stage, the finished matchboxes are carefully grouped into bundles, usually containing 10 or 12 boxes. These bundles are tightly wrapped in transparent polyethylene film, which serves several important functions. First, this packaging protects the matches from moisture, preserving their quality during transportation and long-term storage. Second, it makes the products easier to handle and distribute. After packaging, the bundles are labeled according to logistics requirements. Each package includes information about the manufacturer, production date, batch number, and other necessary details. The products are then arranged on pallets, optimizing transportation efficiency. Loaded pallets are transported to trucks, which deliver the finished matches to stores, wholesale warehouses, or even export them abroad. It is important to note that strict quality control is conducted at every stage of the production process. This ensures that the matches meet high standards and satisfy consumer expectations. The wood's uniformity is checked to ensure it is strong, free of cracks and defects, as it forms the foundation of every match. The durability of the match heads is tested to ensure the chemical composition does not crumble or flake, making the matches reliable for use. The ease of ignition against the abrasive surface is controlled, ensuring matches ignite on the first strike while remaining safe for transportation. Match production is a combination of high-tech equipment, natural raw materials, and strict quality control. Each match goes through dozens of steps before reaching store shelves and, ultimately, your hands. Thanks to automation, eco-friendliness, and safe working conditions, the match industry remains an essential part of many economies. Match production is a complex, multi-stage process that integrates modern high-tech equipment, natural raw materials, and strict control at every stage. The process begins with material preparation, including wood and special chemical mixtures for coating match heads, and ends with packaging the final product. Each individual match undergoes dozens of technological operations, including wood processing, chemical application, drying, and quality inspection before reaching store shelves. Automation and eco-friendly technologies ensure that modern match production meets high safety standards for both workers and the environment. Additionally, manufacturers focus on resource conservation and waste minimization, making the process more sustainable. Matches remain an essential part of everyday life for many people, and their production is an important economic sector that supports traditional industries, creates jobs, and generates stable income for many businesses. By combining advanced technology, sustainability, and a commitment to quality and safety, the match industry continues to thrive in the modern world. It might seem that, in the 21st century, lighters should have completely replaced matches, right? But the reality is not that simple. First, matches are an extremely cheap and compact way to start a fire, requiring no additional costs or recharging. They are also highly convenient for short-term use, such as lighting candles, campfires, or outdoor cooking equipment. Another reason is that matches carry a sense of nostalgia and tradition, often associated with a certain aesthetic or atmosphere. In some cases, they are even used in ceremonies, where this small gesture holds symbolic significance. Safety is another factor. Matches do not have mechanical parts or batteries that can fail. For some users, matches provide greater confidence in reliability. So, the next time you strike a match, remember how many people and machines worked to bring it into your hands. And you know what? They did an amazing job. Imagine this. One ship contains up to 20,000 tons of steel. That's the weight of 3 Eiffel Towers. But what happens when these ocean giants retire? Every year, more than 1,000 vessels are sent for recycling, and their materials find new life in bridges, cars, and even other ships. This isn't just dismantling, it's giving metal a second life. Stick around to see how this global process is changing the world. The beginning of the end, or why are ships dismantled? Ocean vessels have an expiration date. On average, that's about 25 to 30 years. After this, maintaining them becomes uneconomical and their structures unsafe. This is where a process, often called shipbreaking, begins. Remember those movie scenes where ships are shattered by waves? Well, no waves are needed here. Just welding tools, massive cranes, and teams of workers who know how to handle these metal giants. First, everything is stripped from the ship. Furniture, electronics, pipes, and cables. Even doors and windows. All of this can be recycled or reused. This process is usually carried out by hand, though sometimes specialized equipment is used. Workers physically dismantle the interior of the ship, unscrewing bolts, cutting metal pipes, removing doors, windows, and panels. It's meticulous, labor-intensive work, requiring attention to detail and strict safety protocols. Imagine this. Cables need to be carefully extracted so they can be sold as copper scrap, and chemicals, such as leftover paint or lubricants, must be safely removed. Even furniture is taken apart to salvage wood or metal components. Of course, on large shipyards, workers are aided by mechanical tools, cranes, gas cutters, and sometimes robots to handle hazardous materials. But the bulk of the work is manual labor. That's why, in countries like Bangladesh or India, where labor is cheaper, shipbreaking is so popular. This stage is crucial because properly preparing a ship for dismantling prevents leaks of chemicals and toxic materials that could harm the ecosystem. Oil, fuel, and chemicals all are drained from the ship to avoid environmental contamination. Once the ship's hull is stripped of everything unnecessary, the gas cutters take center stage. Massive, rusty steel walls, the very structures that once kept the ship afloat, are gradually turned into individual pieces of metal. Workers, dressed in protective suits, stand directly on the hull. Their cutters create bright orange sparks, flying in all directions, producing a kind of steel fireworks. It's both mesmerizing and slightly intimidating. The cutter heats the metal to such a high temperature that it literally melts. But it only looks easy. Ships aren't just piles of steel. They're labyrinths of multiple layers of metal. Sometimes workers have to cut through several layers to reach the right spot. Cutting begins with the upper decks. Large sections are first carved out, like chunks of sidewalls, decks, or even parts of the hull, which are then lifted by cranes and loaded onto platforms. From there, they're sent to factories, where the pieces are recycled into new steel or aluminum. But it's not just about cutting, it's about doing it safely. That's why the hull was cleared earlier of any leftover fuel, lubricants, or other hazardous materials. Without this step, gas cutters could trigger explosions. So, this process is not just labor, it's an art that requires strict adherence to safety rules. And of course, all this happens under the blazing sun or in humid coastal climates. Workers quickly adapt to the heat, and even sparks flying at their feet become a routine sight. In the end, they witness the transformation of a massive, once indomitable ship into mere pieces of metal. It's almost like watching a rebirth. Imagine this. Those massive steel blocks that once kept a ship afloat become the foundation for new bridges, buildings, or even other ships. About 90% of a ship's materials can be recycled, and the largest share is steel. A single large ship can yield up to 20,000 tons of this metal. That's the equivalent of 3 Eiffel Towers in weight. Once the ship's hull is cut into pieces, the next thrilling phase begins: transporting the steel to factories. And trust me, it's not as simple as throwing it on a truck and driving off. These metal pieces are usually so large and heavy that they can't be moved by conventional means. Massive cranes, the kind that look like they could lift a ship themselves, dominate the scene. Their long metal arms with hooks or magnetic platforms carefully grab steel sections and lift them off the ground. It's almost like watching giant toys in action, but everything is done with surgical precision, because one mistake could be costly. After that, the steel is loaded onto huge platforms or special trucks. Regular trailers won't cut it here. You need vehicles with reinforced frames capable of bearing tons of weight. Imagine this: one section can weigh several dozen tons. Sometimes, rail cars or barges are used for transport if the factory is near a port or river. This helps cut down on delivery costs because moving steel is no cheap task. The journey to the factory can be long. For example, if a ship is dismantled somewhere in South Asia, its materials might be sent as far as Europe or America. In such cases, the metal is loaded onto ships again, but this time on cargo vessels. Full circle, right? A ship becomes raw material transported by another ship. Once at the factory, the metal is carefully weighed. Every detail matters, from the total weight to the precise composition of the metal, as different alloys require different processing. Only then does the steel head to the melting stage, where its new life begins. This steel will become new construction materials. Ships continue their legacy, not in the ocean, but as skyscrapers or train tracks. But it's not just steel that's valuable. Ship components also contain aluminum, used in car and airplane manufacturing. Wooden elements, rare in modern ships but present in older ones, are restored and sold for decor. Fabric from old seats is sometimes repurposed into bags or even rugs. Isn't that cool? You buy something stylish and later find out, oh, this was on a liner that sailed the Caribbean. But it's not all smooth sailing. Ship recycling can pose environmental risks if done irresponsibly. Ever heard of Alang? It's the world's largest ship recycling yard, located in India. There, ships are literally beached and dismantled by hand. This method is cheap, but dangerous. Oil and chemicals can leak into the water, and workers often lack proper protective gear. Recently, however, the world has started paying attention to this issue. More and more ships are being recycled at specialized yards that follow strict environmental standards. For instance, in Europe, regulations require the safe storage and disposal of hazardous materials. The largest ship ever dismantled was a container vessel measuring 1,312 feet in length. Imagine taking apart such a giant. This container ship, Ever Given, became famous in 2021 after blocking the Suez Canal, though its end wasn't due to that incident. When ships of this scale are retired, they're usually sent to one of the world's biggest shipbreaking capitals. Dismantling such a vessel likely took no less than a year, because a mountain of steel, cables, equipment, and other materials is a serious challenge, even for experienced teams. Every piece must not only be cut, but also carefully moved, sorted, and shipped for recycling. At the steel plant I visited, everything starts with thoroughly inspecting the metal pieces. They're cleaned of any paint, rust, lubricants, or other impurities that could affect the quality of the steel. Watch as dozens of hands and machines work to prepare this metal for its next journey. Next, the pieces are shredded, cut into smaller parts that are easier to load into the smelting furnace. The process of cutting metal at steel plants is a spectacle in itself, like something out of a sci-fi movie. Huge workshops filled with sparks, heat, and the hum of machinery. These aren't ordinary scissors. They're powerful hydraulic presses, cutting machines, and even lasers. Each tool plays its part depending on the size and type of metal. First up are hydraulic shears. These massive machines can slice through thick steel like paper. They operate under immense pressure, thousands of tons of force that literally crush and cut the metal. Their crunch echoes throughout the workshop. For finer work, gas or plasma cutters are used. A gas cutter operates by burning fuel. Oxygen and acetylene heat the metal until it melts, and then a stream of gas cuts through it. Plasma cutters are even cooler. They create an electric arc that melts the metal, leaving a clean, precise edge. Then there are laser machines. They work with incredible precision, carving out the tiniest details. The laser beam seems to dance across the metal's surface, leaving behind a smooth, polished cut. This is the technology of the future, already in action at many factories. But this isn't just random cutting. Every step is carefully planned. Metal is sorted by thickness and type to avoid damaging equipment. Larger pieces go through specialized conveyors to the next stage, while smaller ones are sent straight to melting. For melting steel, arc furnaces are used. These massive monsters run on electricity, generating temperatures close to 3,000 degrees Fahrenheit. The metal simply melts, transforming into liquid steel. But that's not all. Special substances, known as ferroalloys, are added to the molten mass to enhance the steel's properties. Need strength? Add vanadium or chromium. Want it lightweight? Add aluminum. It's like cooking, but for engineers. Next, the steel is poured into molds, depending on what it's destined to become. These could be sheets, beams, rebar, or even wire. The castings are cooled, cut, polished, and then shipped off for new projects. Building skyscrapers, bridges, or even new ships, all of this can start with the recycled hull of an old vessel. And isn't it amazing? A ship that once carried thousands of tons of cargo across oceans can become part of a car or the frame for a modern stadium. This second life of steel feels almost magical, doesn't it? There are more than 5 trillion pieces of plastic floating in our oceans, and this number keeps growing every single day. Turning trash into something useful isn't just a creative idea, it's an absolute necessity. This approach not only reduces harm to nature, but also proves that even the worst garbage can have a second life. Imagine this, that waste could be turned into something as stylish as sneakers. Surprised? Well, let's dive into this fascinating journey together. First, you need to find the trash. Specialized organizations rely on advanced collection systems to do this. Hunting for ocean trash is an impressive and highly technical process, using cutting-edge tools designed to capture plastic. One of the most renowned organizations tackling this issue is the Ocean Cleanup. They deploy massive floating barriers that are strategically placed in ocean currents, where plastic waste tends to accumulate in large garbage patches, zones of concentrated trash. Here's how these traps work. Large floating structures equipped with nets or barrier walls move through the water, capturing plastic that drifts into their range. These systems are designed to catch plastic debris floating on the surface, as well as some submerged deeper in the water. Imagine enormous nets gliding smoothly through the ocean, sweeping up all kinds of waste in their path. Once the trap is full, it's hauled to a specialized vessel, where the collected plastic is unloaded. This is done using massive mechanical cranes or conveyor belt systems. The unloaded waste is then sorted and cleaned to prepare it for recycling. These technologies don't just clean up our oceans, they create opportunities to repurpose plastic into new products like textiles, sneakers, and even construction materials. The sight of machines pulling massive piles of trash from the water is both inspiring and a little shocking. Plastic of all shapes and sizes, bottles, bags, broken fragments, and even old toys is brought ashore for sorting. It's a stark reminder of the scale of the problem, but also a glimpse of the incredible potential for change. Once the trash is unloaded onto the ship, it's transported to the nearest port. On land, specialized facilities equipped with conveyor belts and robotic sorting systems take over the next stage of processing. Here, the waste is sorted, cleaned, and prepared for recycling. The process moves at an incredible pace. Robotic arms sort the plastic by type, like assembling a massive jigsaw puzzle. This isn't just random sorting. Advanced technology can detect even the tiniest pieces of plastic. After sorting, the trash gets washed. Much of it is covered in algae or other organic matter, so cleaning is a messy but absolutely crucial step. Sorting is followed by a multi-step washing process. First, the waste is rinsed or scrubbed to remove large contaminants like sand or dirt. Mechanical systems, such as conveyor belts, move the trash through brushes or nets that scrape off big debris. Next, the smaller impurities like oil residues or fine dirt are removed. This can be done in several ways. For instance, as the trash moves along a conveyor belt, high-pressure sprayers rinse it with water. The jets dislodge grime, organic residues, and oil stains. Another method involves submerging the waste in water tanks. These tanks often feature circulating currents, which enhance the cleaning process by gently agitating the plastic and rinsing away remaining dirt. To tackle oil contamination, the plastic is treated with specialized cleaning solutions or chemicals that break down petroleum products and other stubborn pollutants. After these stages, the plastic is finally ready for recycling or disposal. The water used in the cleaning process typically undergoes filtration, so it can be reused or sent for purification to reduce environmental impact. This precise and efficient system ensures the waste is clean and ready for the next step, with adjustments made depending on the material type and its level of contamination. The process of shredding and melting cleaned ocean plastic is truly mesmerizing, a real choreography of technology where each step amazes with its scale and precision. Enormous machines, resembling giant blenders, slice, grind, and crush the plastic into tiny granules. These powerful devices, equipped with massive blades and cutting tools, work at incredible speeds, creating an artificial snow of microscopic plastic particles. As mentioned earlier, the scale of this operation is astonishing. These machines can shred over 1,000 pounds of plastic per hour. The shredded material is ground into granules, which are then sent for melting at temperatures around 500 degrees Fahrenheit. For context, this is the point at which most types of plastic begin to melt and become pliable for reshaping. The roar of massive grinding discs and the compressed sounds of mechanical force fill the air as the plastic is transformed into tiny granules that shoot through the air. Different types of plastic are blended and shredded into a uniform mass. This isn't just waste, it's raw material, ready to be turned into something new. While the granules vary in size, each one is precisely prepared for the next step: melting. These shredded particles are then sent into industrial furnaces for a dramatic transformation. The melting process is comparable to dough that starts off hard and crumbly, but becomes soft and elastic under heat. Gigantic furnaces, heated to extreme temperatures, melt the plastic into a thick, almost liquid state. This molten plastic flows through pipes, gleaming under factory lights like a fiery river coursing through the corridors. In that moment, everything around feels almost magically alive. The melting technology is much like what happens when chocolate or wax is melted into a liquid form. Plastic doesn't just soften, it becomes flexible and easy to shape. At this stage, it's ready to be molded into new items. This semi-liquid material, balanced between solid and fluid states, represents the start of something new, a material reborn to re-enter the cycle of life. As the molten plastic cools, it hardens and takes shape, transforming into products that become part of our everyday lives. This is one of the most captivating stages of recycling, where simple trash turns into something useful, once again finding its place in the world around us. Adidas, Parley for the Oceans, and other brands are already turning ocean plastic into stylish products. For example, making sneakers out of this plastic looks like something straight out of a futuristic lab. Liquid plastic is poured into molds, where it hardens to form the perfect sole. The upper part of the shoe is woven from recycled plastic threads, a kind of textile wizardry that transforms trash into a fashionable accessory. Here's a fun fact. Producing just one pair of sneakers can use up to 11 plastic bottles. These sneakers are not only stylish but also eco-friendly, utilizing materials that might have ended up polluting our oceans. On a large scale, recycling plastic helps reduce dependence on virgin resources. For instance, recycling 1 ton of plastic cuts carbon dioxide emissions by as much as 1.5 tons. One of the biggest names in sportswear even created jerseys for soccer teams, including Real Madrid, made from plastic retrieved from the ocean. Now, players are quite literally wearing the ocean during their matches. What about construction materials? This is another equally fascinating avenue. Plastic granules are mixed with sand or other materials to create durable panels for construction. Ever considered that your home could be partly built from recycled trash? This is becoming a reality, not only reducing the amount of plastic in our oceans, but also cutting carbon emissions in the construction industry. In New Zealand, plastic bottles are being turned into synthetic sand for building roads. This sand is significantly cheaper and more eco-friendly than traditional options. Here's a staggering statistic. Every minute, more than 2,000 plastic bottles enter our oceans and seas. Only about 9% of all plastic waste in the environment is properly recycled. The rest ends up in landfills or the ocean, leaving us with serious concerns about the planet's future. But there's good news. Recycling ocean plastic isn't just about helping nature. It's also a booming business. For example, one company specializing in ocean plastic recycling processes over 22 million pounds of plastic each year, transforming it into sportswear and accessories. In the fashion industry alone, more than 500 million plastic bottles are reused annually to create new products. Many companies are repurposing old fishing nets, which pollute the oceans, into sneaker soles. These fish catchers are now turning into eye catchers when you slip on these stylish kicks. Some companies even craft trendy chairs from ocean plastic, including discarded fishing nets. The irony? These nets used to catch fish, and now they sit in restaurants.